First of all, welcome to the course Properties of Matter. I would like to divide this into two parts, which will consist of fluid mechanics and some mechanical properties of matter. We'll solve some questions in between and at the end. So now I would like to describe what do we mean by fluids. If we see this table, it has solids, liquids and gases divided in some properties according to some properties. Now the property of flow is only there for liquids and gases. And that's why we call them fluids. Now some assumptions we are going to make are, first of all, we are just considering incompressible, steady and non-viscous fluids for this particular chapter. For the next section there will be viscous forces too. Now coming to the calculation of pressure, first of all let us define pressure. The pressure at a point A is given by limit delta S tends to 0 F upon delta S. Now delta S is a small area which is randomly oriented around the point A.
So delta S appears to be a two-dimensional disk of sorts.
Yes, right, correct. Now in a homogeneous non-viscous fluid, delta S का orientation matter नहीं करेगा. So अब हम देखते हैं कि units, the SI units of pressure are Newton per meter square. This is also called Pascal. Coming to the variation of pressure with height, the pressure at a lower point P1 and between a higher point P2, we'll have the pressure difference P1 minus P2 is equal to rho GH in the same fluid. Rho is the density of fluid, G is the acceleration due to gravity, and H is the distance between the two. Horizontal variation of pressure is given by P1 is equal to P2 for 2 points at the same horizontal level in a particular fluid.
So the next topic is Pascal's law.
तो पास्कल्स लॉ को हम ऐसे डिफाइन करते हैं कि अगर प्रेशर इन अ लिक्विड को किसी एक पॉइंट पर चेंज किया जाए तो वो सेम प्रेशर लिक्विड के हर भाग में ट्रांसमिट होके ऐड हो जाता है. F1 upon A1 is equal to F2 upon A2 for two different points in a fluid. इसका एग्जाम्पल हमें क्वेश्चन से बाद में देखेंगे. अब बात करते हैं एटमॉस्फेरिक प्रेशर की. एटमॉस्फेरिक प्रेशर P0 is equal to PATM is equal to 1.01 into 10 to the power 5 pascals. Now, P0 is defined as integral 0 to Z, where Z is the height of the atmosphere, rho air G dz. But rho air is not a constant and there are height differences. Rho air is a very small quantity and the differences can be ignored. And the height differences for near places is very less. So we can take that in a container, the pressure P0 would be constant. Now we define the working of two meters, barometer and manometer. These are both pressure calculating objects and these are basically governed by these formulas. P0 is equal to rho mercury, this fluid is mercury here, GH, and in a manometer P0 plus rho GH is equal to P1.
और दोनों में mercury है.
इसमें कोई भी लिक्विड ले सकते हैं और इसमें नॉर्मली मर्क्यूरी या अल्कोहल लिया जाता है. आर्किमिडीज प्रिंसिपल. आर्किमिडीज प्रिंसिपल ये कहता है कि अगर एक फ्लूइड के अंदर हम किसी ऑब्जेक्ट को रखें तो उस पे ऊपर फोर्स ऑफ बॉयंसी लगता है विच इज इक्वल टू डेंसिटी ऑफ फ्लूइड, इस फ्लूइड की डेंसिटी और वॉल्यूम डिस्प्लेस बाय दिस ऑब्जेक्ट. तो फ्लूइड की डेंसिटी होगी और वॉल्यूम डिस्प्लेस बाय द ऑब्जेक्ट होगा इनटू जी. यहाँ ध्यान रखने वाली बात यह है कि रो फ्लूइड का लिया जाता है.
So let's begin the next thing, that is horizontal force.
Horizontal force on a randomly oriented object inside a fluid F horizontal is given as pressure at the center of mass of the object into area of projection of this object on the vertical plane. For example, there is this rod which is at an angle theta. If we take the projection on the vertical, it will be this area. This area multiplied by the pressure at the CM will give us the horizontal force on the object.
अच्छा, अभी मान लीजिए ये फ्लूइड ऊपर की तरफ फ्लो हो रहा था, तो ये क्वेश्चन मतलब जो आपने एरिया ढूंढा है ये कैसे चेंज होगा?
Here we are not talking about the flow of the liquid.
Okay.
This is a static case where the fluid is static.
Okay, fine.
Yeah. Now we talk about the acceleration. जब नीचे G लग रहा था, when the fluid was static, so we had the surface perpendicular to the gravitational force.
ठीक है.
In the same way, if we have other accelerations
अच्छा.
and we consider pseudo force, like जैसे कि हम एक चींटी बन के इस कंटेनर पे बैठ गए जो एक्सेलरेशन A से आगे जा रहा था, तो हमारी फ्रेम में इस वाले फ्लूइड पे कोई फोर्स नहीं है.
ठीक है.
लेकिन सूडो फोर्स लग रहा है क्योंकि एक एक्सेलरेशन दिख रहा है.
ठीक है.
सो दिस विल बी द A pseudo which has the same direction as negative of the force A.
ठीक है.
And the force G. This will result in a net force of A resultant.
ठीक है.
And the pressure between point P1 and P2 would be rho A resultant into H dash, where H dash is the distance from the surface of the fluid to another point in the fluid in the direction of A resultant.
Okay, so let's begin the continuity equation.
Yeah, so the continuity equation and the Bernoulli's equation will also have the same assumptions we had for the other parts of this chapter.
Okay.
That is steady flow,
Okay.
irrotational flow. irrotational flow आप कैसे समझ सकते हैं कि जैसे एक नदी में या एक तालाब में जैसे भंवर होता है, that is rotational flow.
ठीक है.
So irrotational flow would be that no net angular velocity to any particle.
ठीक है.
And with the other assumptions, we have the continuity equation A1 V1 is equal to A2 V2. A1 is the area at a particular point and V1 is the velocity at that same point.
Okay.
And at another point, the area and the velocity in the same flow will be equal. So A1 V1 is equal to A2 V2.
Fine.
Coming to the Bernoulli's equation, we derive it by the work energy theorem, which says that work done on a particle by a resultant force is equal to change in kinetic energy of the particle.
Okay.
Like continuity equation can be said to be the conservation of mass, this can be said to be the conservation of energy.
अच्छा.
So this rule says that rho gh plus p plus half rho v square is equal to constant for two parts of the same flow.
Okay.
For example, if we have this pipe, the velocity here is v1, here is v2, pressure here p1, p2, and the height h1 and the height here is h2.
Okay.
So rho g h1 plus p1 plus half rho v1 square is equal to rho g h2 plus p2 plus half rho v2 square.
Fine.
The applications for the Bernoulli's and the continuity equation in efflux moving out of liquid from a small area below the container.
ठीक है.
So if area A2 is very small then as compared to A1, V2 the velocity from here would be equal to root 2 gh.
ठीक है.
Venturi tube is used to measure the velocity of fluids at different parts.
अच्छा.
It has varying lengths and therefore the velocity v1 and v2 would be different.
Okay.
So the formula for this is 2gh equal to v2 square minus v1 square.
अच्छा. Fine.
Right. And the h is the difference between these two levels of fluids.
ठीक है.
Aspirator pump. Surprise, I'm not going to explain this. बेगॉन याद है, पुराने बेगॉन में एस्पिरेटर पंप होता था. JEE 2014 क्वेश्चन है, we'll solve it by the end of the chapter.
So let's start with the next part of this topic, that is mechanical properties of matter.
Yeah, so first of all, matter is made up of molecules and atoms. Molecules are in turn made up of atoms. Atoms can be made up of nucleus and electrons. There are forces, electromagnetic forces between the two of these, which governs the structure of an atom. And there are protons and neutrons which make up the nucleus, which are governed by the nuclear forces. But what we are interested in is electromagnetic intermolecular forces, the forces between the molecules which govern the structure of matter. Now, describing the forces and the intermolecular distance, we have a particular graph. U is the potential energy between two molecules, yes.
Okay.
And F is equal to minus du by dr.
Fine.
Stress. Now, we define two kinds of stress over here, normal stress and shearing stress.
Okay.
We take up an area, a small area delta S, which is randomly oriented.
Okay.
Fn is forces which are perpendicular to delta S, and Ft is tangential to delta S.
ठीक है.
Normal stress or longitudinal stress is equal to forces which are perpendicular to delta S upon delta S, and shearing stress is given as forces tangential upon delta S.
अच्छा, तो ये फिगर में Fn और Ft कहाँ होंगे?
फिगर में Fn और Ft, Fn would be the sum of forces in this direction,
ठीक है.
and Ft would be the sum of forces in the perpendicular direction.
ठीक है. तो let's move on to the next topic, which is strain.
Yeah. Strain. Longitudinal strain is defined as the change in length delta L upon L on application of normal forces. This can be either tensile or compressive. Shearing stress. Shearing strain is defined by taking a small area ABCD
Okay.
and giving it four forces which are shown here in the black.
Okay. So this square is an like an atom or a molecule of a large object.
This is an area of a large object, a small area of a large object.
Okay, fine.
Yeah, so if given these four forces, translational and rotational equilibrium would be there.
Okay.
But the body will deform in a way which makes it look like A dash, B dash, C dash, D dash.
Okay, so something like this diamond shape over here.
Yes.
Okay.
And we define shearing strain as X is equal to H in the following figure, where we have turned this particular A dash, B dash, C dash, D dash and matched A dash and D dash to the earlier AD.
Okay, fine.
Volume stress is defined as tau V is equal to F upon A. F is perpendicular to the area, and volume strain is defined as del V upon V.
Okay, fine. Where delta V is the change in volume, right?
Yes.
Okay, fine.
Now Hooke's law and modulus of elasticity. So for normal stress and strain, stress is proportional to strain, and this proportionality constant, which is shown Y over here, is the modulus of elasticity. Okay. Which is constant for a particular material.
Fine.
And it will be given by obviously stress upon strain. So F upon A upon is upon delta L upon L, which is equal to FL upon area into change in length.
Fine. So this will be the constant. Okay.
Yeah. Now we come to shear modulus, or we call it modulus of rigidity or torsional modulus. In the same way we defined normal stress, we define it as stress upon strain. But here the stress would be the shearing stress and the strain would be the shearing strain.
Okay, fine.
We can also refer to the diagram above.
Okay, that is the diamond one which you were referring to before.
Yes.
The next type of modulus is bulk modulus.
Yeah, bulk modulus is defined for an object inside a fluid. B is equal to minus of pressure upon change in volume upon volume. Since we want B to be positive, as it is a constant, we add this negative sign on the RHS, which was required क्योंकि pressure आने के कारण delta V negative होगा.
ठीक है, fine.
Right. So now we define the Poisson's ratio. We haven't taken into the account the change in area which comes along with the extension in length on application of forces.
Okay.
But in the Poisson's ratio, this is exactly what we define. So Poisson's ratio is equal to minus of change in the diameter upon the diameter upon the change in length upon the length.
Okay, fine. So basically the Poisson's ratio is change in diameter by the original dimension and
yes.
the similar ratio but for the length.
Yes.
Right?
Right.
Okay, so let's move on to the stress curve.
Yeah, so this is the stress strain curve for a metal wire. This is important because we can analyze a lot using this. Metal wire A For a metal wire, the A is the proportionality limit, which means that the Hooke's law is valid till A. B is the yielding point, D is the fracture point. 0 to A would be the proportional or the Hooke's law part. A to B would be elastic but not proportional. This means that the object will regain the shape, but the stress will not be proportional to the strain.
Okay.
B to D would be the plastic behavior. That is, the object will not try to regain its shape. The C part here is the permanent deformation, which will be equal to the X as shown here.
Fine.
Now we define the formula for elastic potential energy. It is equal to half into stress into strain up into volume when slowly stretched and ignoring area deformations.
Okay, fine.
Young's modulus experiment. We don't cover much of this as it is covered in the units and dimensions. We just have to remember the formula. Y is equal to mg capital L, that is the original length, upon pi r square into small l, that is the change in length.
Okay, fine. So basically delta L of sorts.
Yes.
Fine.
So surface tension. Now we come to a very important topic called the surface tension. So surface tension is defined as the force upon length. The length here is the contact length of two different surfaces.
Let's start with the next subtopic, that is capillary rise.
Capillary rise is the basic application of surface tension which we just studied. So if we balance the forces, that is the force of gravitation on this part of the liquid, the pressure differences between the 2 points, and the surface tension force which is given by this, then we'll have the height which rises inside the small tube or the capillary is equal to 2 into s cos theta upon r rho g.
Okay, and what are the forces when we are analyzing and looking for H?
So the forces would be gravitational force, the pressure difference, and the force due to surface tension.
Achha. And what is theta?
Now theta is a very important concept. Angle theta is the angle which the surface tension force makes with the vertical axis. If contact angle is greater than 90 degrees or the surface of the liquid looks something like this inside the capillary, then it would mean that F1, the force due to surface tension, would act downwards.
Fine.
If the contact angle is 0, instead of the formula which we had previously, we can add this term as a correction for the area which is given by the red markings over here.
Okay, fine. So basically what we've seen here is for different angles of theta, how the meniscus is going to look, and hence how the forces will be or the height of the meniscus will be.
Yes.
So let's move on to viscosity now.
Yeah. So viscosity. The force of viscosity is like friction in solids. Now viscosity in liquids is between the surfaces of the liquid.
So basically between layers of fluid.
Yes. So fine. F is equal to minus eta A dV upon dz. Now dV upon dz is the velocity gradient. Using this, we'll solve a question to clear this out a bit more.
Okay, fine.
Now the Poiseuille's equation is for a pipe with viscous flowing liquid and a pressure difference P. And it is given as the volume upon time is equal to pi into pressure difference r to the power 4, r is the radius of the tube, upon 8 eta L.
And is the pipe meant to be horizontal when applying this equation?
Yes, it has been approximated and it is meant to be horizontal.
Next.
Stokes law. Now Stokes law is defined for a spherical body of radius r at speed v in a fluid of viscosity eta. F is proportional to v. This is basically the Stokes law. So F is proportional to v and the constant is given by 6 pi eta r. So we have the formula F equal to 6 pi eta rv, that is the viscous force on a spherical body would be equal to 6 pi eta rv.
Fine. Where eta is the viscosity.
Yes, and this force acts upwards.
Okay, fine.
Now, because we have a viscous force acting upwards, buoyancy acting upwards, and gravity acting downwards, viscous force is proportional to the velocity.
Okay.
If velocity increases to a level such that the forces balance, we'll have a particular velocity at which the acceleration becomes zero.
Oh, okay.
This is called the terminal velocity.
अच्छा.
ठीक है, तो अब v नॉट या टर्मिनल वेलोसिटी को हम लिखते हैं 2r स्क्वायर रो माइनस सिग्मा g अपॉन 9 ईटा.
ठीक है.
सिग्मा को नॉर्मली इग्नोर कर दिया जाता है क्योंकि ये डेंसिटी ऑफ लिक्विड है, एंड वी नॉर्मली निग्लेक्ट दिस बिकॉज इट इज स्मॉलर एज कंपेयर टू द डेंसिटी ऑफ द बॉडी.
ठीक है.
एंड r is the radius of sphere.
अच्छा.
What we should mark here is that this formula is also for spherical bodies only.
ठीक है.
Coming to the Reynolds number. Now, this is just a formula which is given in some books. N is equal to rho Vd upon eta. Smaller values than 2000 for N will give us a steady flow. Greater than 3000 will mean turbulent, and 2 to 3000 will mean unstable. Here,
And what is the application of this Reynolds number?
yeah, if we see the flow in a pipe with a diameter capital D,
Uh-huh.
so if rho Vd upon eta, V is the velocity, rho is the density, and eta is the viscosity.
Okay.
So if we find out this particular number n, which is a dimensionless quantity,
Okay.
it will tell us the type of the flow. It can be steady, turbulent, or unstable.
Okay. Fine. Question 1. The liquids shown in the figure in the two arms are mercury and water. If the difference of heights of the mercury column is 2 centimeters, find the height h of the water column. तो इस क्वेश्चन को टैकल करने का हमारा क्या अप्रोच होने वाला है?
इस क्वेश्चन को देखते से ही हमें सबसे पहले ये समझ में आ जाना चाहिए कि प्रेशर को इक्वेट करना पड़ेगा. अब प्रेशर को इक्वेट करते समय हमें पहले ये डिसाइड करना पड़ेगा कि किन पॉइंट्स पर. तो हम एक पॉइंट लेते हैं ए, जो वाटर और मर्क्यूरी का कॉन्टैक्ट सरफेस है.
ओके.
और उसी के हॉरिजॉन्टल, सेम हॉरिजॉन्टल लेवल पे बी.
ठीक है.
अब क्योंकि एक ही फ्लूइड में सेम हॉरिजॉन्टल लेवल पे P1 इज इक्वल टू P2 होता है,
हाँ,
जैसा कि हमने पढ़ा था,
हाँ,
तो प्रेशर एट पॉइंट ए वुड बी इक्वल टू प्रेशर एट पॉइंट बी.
ठीक है.
नाउ प्रेशर एट पॉइंट ए वुड बी द प्रेशर of atmospheric pressure P0 plus the pressure which is there because of the water column, which should be equal to rho water into G into H.
ठीक है.
Now, rho water you should remember rho water, and the value for rho water is 1000 kg per meter cube.
Okay.
And G is obviously gravitation, which we take as 10. And H is to be found out. While we write the pressure at point B, it would be equal to P0, obviously, because here also the pressure of atmosphere is in contact, plus rho of mercury into G into H, which is equal to, see, rho of mercury is basically specific gravity into rho of water.
Okay.
So this would be equal to P0 plus 0.02, that is the height of the mercury column,
okay,
in meters, into 13600,
okay,
into G.
Fine.
Now simply calculating this by putting in the values and equating PA is equal to PB, we get H is equal to 0.02 into 13.6, that is 27 centimeters.
Okay, fine. So let's do a quick recap of how we solve this question. So the question has given us apparatus wherein there is mercury and water.
Yes.
And what we are charged to do is find out the height of the water column.
Yes.
So what we have done is selected two suitable points at the same horizontal level to ensure that their pressure will be the same.
Yes. And in the same fluid also. Like this is in the same fluid mercury.
Okay, fine. So another pointer for selecting suitable points is they must be in the same fluid as well.
Yes.
And then we found out the pressure at both the points, equated them, and this resulted in finding the answer, that is h, which is equal to 27 centimeters.
Yes.
Question 2. The experimental setup is given as shown. We have A and B being on the same horizontal level. Side B has a massless platform with an area of 4 meters square with a load of 20 kilograms on it. Side A has a piston of cross-sectional area of 400 centimeters square with a mass of 10 grams. The question demands that we find the extra force one has to apply on side A to just lift the mass on the other side. So what is going to be our approach for this question?
Yes. First of all, like we did in the last question, we had atmospheric pressure at both of the surfaces at equal horizontal levels.
ठीक है.
But here, that is not the case. Here we have some forces acting on the top of the both of these parts of the fluid.
Okay.
So now we have to use the Pascal's law.
ठीक है.
So the Pascal's law says that if a force F1 acts on an area A1 on one side of the liquid,
Okay.
it would be equal to a force F2 which is acting on another part which has the area A2.
ठीक है.
Now if we apply this over here and F1 and A1 are for the point B, then we get 20g, that is mg, the weight of the object on the side B
ठीक है.
upon the area of cross section there, that is 4 meters square,
ठीक है.
is equal to, on the A side we add up all the forces that we have.
ठीक है.
So first of all we have the mass of the piston, that is 0.01 g. 0.01 because
ओके. वैसे आप अभी तक जो कर रहे थे,
हाँ,
ये पास्कल्स लॉ का डायरेक्ट रिजल्ट होगा, क्योंकि पास्कल्स लॉ ये कहता है कि अगर एक फ्लूइड पे कहीं पे भी प्रेशर एक्स्ट्रा लगाया जा रहा है,
हाँ,
तो वो प्रेशर पूरी फ्लूइड में ट्रांसफर हो जाएगा.
yes,
तो बेसिकली हम लोग ये कह रहे हैं कि ए पे हम लोग जितना प्रेशर लगाएंगे उतना ही बी पे लगाएंगे. और
Yes.
अगर वो सफिशिएंट हो जाए उस मास को उठाने के लिए,
Yes.
तो वो जो फोर्स उससे आएगा दैट विल बी आवर आंसर.
yes, true.
ओके फाइन.
तो 0.01 g हम लोग इसलिए ले रहे हैं क्योंकि ये 10 ग्राम का ऑब्जेक्ट है,
ठीक है.
एंड कन्वर्टिंग इनटू केजी इट विल यील्ड दिस. यूनिट्स आर वेरी इंपॉर्टेंट, सो
ठीक है.
वन मस्ट टेक केयर.
ठीक है.
प्लस एक फोर्स F जो हमने एक्स्ट्रा लगाया और जो हमें फाइंड आउट करना है,
ठीक है.
अपॉन द एरिया ऑफ द क्रॉस सेक्शन हियर, जो कि है 400 सेंटीमीटर स्क्वायर,
अच्छा.
यानी 400 इंटू 10⁻⁻⁴ मीटर स्क्वायर.
ठीक है.
Solving this equation, we get the simple result. F is equal to 0.19 g newtons.
अच्छा, तो इस क्वेश्चन में ये पास्कल्स लॉ लगाने का आइडिया कैसे आएगा?
सबसे पहले हमें देखना चाहिए कि पास्कल्स लॉ हम उन जगह पे लगाते हैं जहां पर हाइड्रोलिक लिफ्ट या फिर किसी लिक्विड सरफेस पर कोई फोर्स के एडिशन की बात हो रही होती है.
अच्छा, ठीक है. तो अगर हमें कुछ उठाना हो फ्लूइड्स यूज करते समय, तो पास्कल्स लॉ सबसे ज्यादा यूजफुल हो सकता है.
एग्जैक्टली. जैसे कि आप देख सकते हैं 20 kg के ऑब्जेक्ट्स को जिसे उठाने के लिए नॉर्मली 20 g फोर्स की जरूरत पड़ेगी, हमें सिर्फ 0.19 g से ये ऑब्जेक्ट लिफ्ट हो सकता है.
अच्छा, तो इसके काफी प्रैक्टिकल एप्लीकेशंस भी हो सकते हैं.
यस.
Okay, so let's just quickly sum up this question. And the question has the given experimental setup with A and B being on the same horizontal level. और B पे कुछ लोड है और हमें वो फोर्स निकालना है जो हमें A पे लगाना होगा ताकि B जस्ट राइज होना शुरू हो जाए.
Yes.
तो हम लोग ने पास्कल्स लॉ लगाया A and B पे, प्रेशर इक्वेट किया, और इस सिंपल इक्वेशन में द ओनली अननोन वाज F, और वो सॉल्व करने पे हमें आया 0.19 g. So that was answer to it.